Hey guys, welcome to week 21. We're going to go through an intro into microcontrollers with the goal of trying to link our already familiar Arduino Nanos from the Introduction to Electronics boxes to STM32 microcontrollers. We'll go through reading out the pinout schematics of microcontrollers, understanding the workings of digital pins, analog pins, and basic communication protocols.
All right, so yes, as Will mentioned, he's going to take you through the Arduino, actually the Arduino micros this week, which is really exciting. So Will is a Curtin engineering graduate, mechatronics, and has done both the tertiary spacecraft project and space systems design programs here at Curtin University, and he is the one that is helping me answer all of your emails that you've been sending through on your sensors and your circuits and all those technical questions that he has a little bit more expertise. So he's been fantastic, and he really loves teaching. So before he gets stuck into his session this week, I'm going to share all of the awesomeness that's been happening at the Binar Space Program over the last couple of weeks because it's been huge. So you've been following along, but first thing we'll share is that Catherine Bennell-Pegg, Australia's first astronaut, came and visited the Binar Space Program labs and offices, as well as students at Curtin University. And we got to have her tell her story to us and share what work we had done. And Nick Rogers is there on the left, handing her one of our Binar 234 mission patch stickers that he designed that some of you may have. If you want one, let me know. So she loved that because everyone loves a good mission patch. It's very much a space program thing. And then on the right there, Kyle McMullen is sharing his PhD work on his shape memory alloy, which are on our deployable solar panels and the work that he's done. And in fact, those have deployed successfully and stretched out, and our Binar 2, 3, and 4 that are right in orbit right now are recharging successfully. So that was great for him to be able to share with Catherine. So I got to meet her as well, and just really was so proud to share the story of all of you students and teachers doing the work in the BinarX program. Catherine thought it was amazing that high school students were building instruments and payloads for space flight and experiments, and she was kind enough to take some time and write a special message to all of you in a copy of our How Space Works book. So that's the copy that we have here at Curtin, but I couldn't get her to sign all the copies, so I got her to sign one and share that special message with you because she understands, this is a hard thing that we're doing and that you're doing, and so persevere. And that's summed up really nicely in the message that Catherine's written. If you can read it there on the left, I took a photo of it. To the BinarX students, keep doing hard, amazing things. To the stars, Catherine. So that was really, really awesome. So that's something that we'll treasure in the program, and that you can know that she's sending that message to you. And there she is with our team, so standing outside the T.L. Robertson Library, just behind the Binar Space Program lab. She really took some time to visit with us, so that was awesome. And then the very next day, we had our team, past and present, members of the community gather at Curtin Hive, which is the hub for immersive visualization, to actually watch and give the command for our satellites to be deployed from the International Space Station into orbit. So the team is watching on. On the right, you can see myself and Mia Walker with BinarX student Pema in the middle. So shout out Pema for coming all the way down again and coming and seeing the launch. That was awesome, or the deployment rather. And there on the right, there on the left, you can see the successful deployment of Binar 2, 3, and 4 into orbit from the JSOD deployer, which is on the Kibo module on the ISS, and some very, very excited faces there on the right as we saw them all come out. So thank you to JAXA for these photos and some that are coming up, and Ezra Alcantara, who's our photographer, who's been capturing all the lovely photos of all the milestone days and mission concept review. So he does wonderful work and really captures those photos. And you may have noticed the cover for this week's slide deck is a little bit different from the one you're used to seeing, and that's because JAXA has taken some beautiful images of the deployment and flight, first moments of flight of Binar 234 in orbit from the ISS. And there on the left, that's the moment of deployment, a little bit much higher resolution than the live stream. And you can see 2, 3, and 4 all coming out. And then on the right, just a beautiful photo of 2 and 3 sticking close together on their first few meters out of the space station, and 4 behind. And then behind is the solar panels at the International Space Station and our planet below, and you can see that beautiful atmospheric glow. So this is a photo that we'll treasure, and look forward to launching your experiments and your payloads and having these kinds of photos when we launch Binar 5, 6, and 7. So keep going. So if you didn't get to watch the deployment live, you can scan that QR code there. That will take you to Jax's YouTube channel where you can watch the replay. And that photo is, again, just after deployment from the ISS of Binar 2, 3, and 4, floating 400 kilometers or so above our planet with the clouds and the ocean beneath. So it was a really beautiful moment. So not only were we celebrating successful deployment, but we also went down straight after because we wanted to listen for the radio beacons of Binar 2, 3, 4 as they did their first pass overhead about 38 minutes after deployment from the ISS. And I won't talk too long over this one, but the very next thing we did was to run downstairs to the Binar office and turn on our ground stage and try and listen for our satellites on their very first pass overhead about 38 minutes later.
Oh, there we go, that's it.
That's all three.
This is our Arduino Nano pinout diagram. It shows all the possible configurations that each pin can have. And to be honest, this diagram has a lot going on, so I think we're going to slowly break it down for you guys. This is the Arduino Nano's microcontroller, the STM32U4. The reason why I included this diagram is so that you guys can compare it to the Arduino's pinout. It's a great exercise because we should notice that the pins match up between both diagrams. This is important because when we move to the STM32s, the configuration interface will look very similar to this. So I've zoomed in a little bit more on the Arduino Nano's pinout diagram. Now we can see clearly the PF7 pin highlighted in red, and we're going to go through each of its configurations and what they can do. So even more zoomed in now, I've got this PF7 pin in isolation. Going from left to right, we've got its ADC channel, its Arduino's default pin configuration, the microcontroller's port ID, the analog pin name, and the digital pin name. Just the microcontroller's port ID is important because if we look between both the pinout for the STM32U8 and this Arduino Nano, we should see that the PF7 links both those pins together. The other three remaining, the ADC channel, the analog pin name, and the digital pin name, I'm now going to go through slowly what each of those mean and what you can use them for. So we're going to go through the digital pin now. It can either be an input or an output. As an input, it takes readings from the pin, and depending on the voltage value, it either returns a 1 or 0, based on where the voltage fits in the figure to the left. VCC, in most cases, is the microcontroller's power supply. The voltage for the Arduino Nano would be 5 volts. The input is sensitive to current and must be protected by a resistor where appropriate. As an output, the microcontroller code can set this pin to high or low, where high is the supply voltage and low is ground. As an output, it can be used to supply a low power signal and shouldn't be used to power devices directly. But as an input, it's commonly used with buttons, switches, state machine variables. Basically, anytime we want the microcontroller to do something after we tell it, and like in multiple different ways. As an output, it tells another component to activate. So this is useful for like sensors, as seen there with the force sensor, another microcontroller. So if we want to turn the switch on to turn another microcontroller to do something, or it can even be used for signal generation. So it can make pulse width modulation waves, which are like square waves. It can even do basic communication protocols depending on how you want to configure it. So on the other hand, what does an analog pin do? Well, it translates continuous analog signals into discrete digital values that the microcontroller can understand and process. These pins are always input pins. You can't output an analog signal from them. And therefore, it will round down to the nearest bit value that corresponds to the continuous voltage value. That's shown in the diagram there, where all those lines are the resolution of the ADC, and it's going to get that lower one and it's convert it into a binary value. And these pins convert this by utilizing that block in the middle, which is the analog to digital converter, otherwise known as an ADC. And what are the characteristics of an ADC? Well, ADCs are bound by two main things. Their maximum voltage, which is normally again bound to the supply voltage, which would be 5 volts in the case of the Arduino Nano, and their resolution, which means the number of bits they have. This number of bits is basically divided evenly through the entire maximum voltage range. So in our case, for the Arduino Nano, it's a 10-bit ADC, which means that it's 2 to the power of 10 possible configurations. So 2 to the power of 10 is 1024. So if you look at that diagram where all those little lines are, there would be 1024 different thresholds between 5 volts and 0, which means you're going to have around 0.01 volts each step, which means you have really nice resolution when you're looking at a sensor, which last week you looked at the temperature sensors. So when you're using the temperature sensor, each step of that resolution, you can convert that back to a degrees value. So the more steps you have, the more accurate you can measure temperature. So what is the 7 in square brackets next to the ADC? Well, this represents the channels of a multiplexer, where if chosen, the ADC will convert that analog value. The diagram that I've drawn here, it shows these channels as an array, where each channel may have a different value, and once read, like for example, with channel 0 having 1024, which means it's reading at 5 volts or more, or for example, channel 1, where having 0 volts, which means it's either 0 or lower. So let's have a more in-depth look at a multiplexer, where if you look to the right-hand side, there's the pins B0, B1, B2, and they select which channel you want to convert, right? So if we had 0, 0, 0, we'd be measuring A0. The B pins are automatically assigned though, so we don't even have to worry about that. So if we say, I want to read A0, then in the background, Arduino is going to set those B pins to 0, 0, 0, or another configuration to get the pin that we want to read. Once that's chosen, as you can see, there's a bunch of like little switches I've drawn there. That switch will connect, and then once it's connected, then that A0 channel that's got the analog signal on it will flow into the multiplexer, and then from the multiplexer, that will flow to the ADC. And then the ADC will convert that analog signal into a digital value that we can read on our Arduino Nano. So lastly, I'm going to go through two basic communication styles, I2C and UART. So I2C can connect multiple peripherals together. It has an SCL, which is the clock line, and an SDA, which is the data line, and they need to communicate back and forth from the controller, which is the Arduino Nano, to the peripheral, which is the sensor. When it's communicating back and forth, there's like this little handshake that it'll automatically do for you to be like, hey, I'm starting communication now, and I'm starting it with peripheral 1 or peripheral 2. On the other hand, the UART has TX and RX lines, which are like the receive and the transmit lines, and then they have a common ground connected together. The TX and the RX lines need to be connected to the opposites. So the transmit of the controller needs to go to the receive of the peripheral, and vice versa. Both of these communication methods are like very useful when you have a sensor that has like digital communication options rather than returning an analog value. So the temperature sensor that we had returns an analog value, which that means we need to use an ADC to read that value, rather than if we had, let's say, like an accelerometer that had communication in I2C back to the microcontroller, which means we need to connect our accelerometer directly back into the I2C pins of the Arduino Nano or the STM32, depending on which microcontroller we use. And then that will receive that information back from the accelerometer that then we can use to either convert it into acceleration values or send that back to the ground station from our flight computer. So now tying it back to the STM32, I introduce you to the F411CEU, which is one of our chips that we might be using for your payload boards. As you can see here, there's like a PB4 pin, PB3 pin, PA15 pin. So those are the same things as like the PF7 pin, which are just the microcontrollers pin IDs. So when you go to code in the STM32 Cube IDE, you're going to be presented with this. No green labels though. So I've gone through and I've assigned a lot of the pins to what we're going to be using. So for example, if you look to the, if you look at my red marker here, there's the ADC1 in on PA0. That's the same as like the A0 pin if we configured it on the microcontroller. And then another thing, GPIO output, which is basically a digital pin output. That's the same as the Arduino. Then we have this debug USART RX and TX. That's our UART communication. So it's all tying in together. Even USART1 RX, that's probably the USART or the UART that connects to our hat boards, which then when you put your chips on your hat board, you can connect that back to the UART pin, and then that will connect back to our microcontroller, which then we can read it, convert the values, do whatever we want, send it to the flight computer, send it down to the ground station. And we're basically there. We've basically finished our desired goal. So to continue with where I was going before, this PB4 pin is a good example where you can see it has the I2C, it has SDIO, it has SPI, which is another communication style. It even has a timer, and then you have your classic GPIO input outputs and analog. These are all the things we just talked about through all the slides. So you can see here that the STM32 has even more possibilities than the Arduino, which makes it a perfect chip for our payload boards. So you can go through and be like, I want this pin to be a GPIO output, or I want this to be an analog read pin, or an ADC pin. Unfortunately, you can't necessarily put every pin to whatever you want, because we've gone and we've made these custom PCB boards or these custom circuit boards, which already basically like fixes you into certain configurations of these pins. So some pins need to be digital, some pins need to be communication, but like if you made your own STM32 board, you could basically have it whatever you wanted, well, in the constraints of what's listed here.
Thanks so much, Will. Great work, and hope you all enjoyed that and that it just gave you a little bit more insight into how the Arduino microcontrollers work. If you're stuck with anything or you're having trouble, I'm sorry I haven't gotten back to everybody's email. We are working through that, and they have been received, so you will get a response, and we'll keep you all moving. And if you're stuck, please just give us an email on binarx@curtin.edu.au. But as much as possible, we'll be really helping focus over the coming weeks on working on your individual payloads and supporting your individual concepts. And next week, the lecture will be to what you're going to include in your preliminary design review presentation, which will be in person at Curtin, just like Mission Concept Review Day, but a bit of a different format on December 2nd, 2024. So that'll be next week, but don't stress, we will support you. And I think over school holidays, there's a 3-week Binar break, so we can work with you kind of one-on-one and individually. There won't be new material, and we can really get those together, and then you can have a rest. Okay, thanks everyone. Have a great week. Bye.